Right now, wherever you are, you probably feel certain about a few things: the screen in front of you, the room around you, the weight of your body, the air you breathe, the solid floor beneath your feet. All of it feels stable, obvious, undeniably real. But what if none of that certainty holds up under closer inspection? What if the physicists who have spent decades probing the edges of reality are starting to conclude something unsettling, something that rewrites everything we thought we knew about existence itself? This isn't about the universe being strange or mysterious. That's been known for generations. What's emerging now from academic journals, physics conferences, and cutting-edge research is far more radical. A growing number of scientists are questioning whether the universe exists at all, at least not in the way we've always imagined. Not as a collection of objects moving through space and time. Not as an objective reality that would continue unchanged if no one were here to witness it. Instead, what if everything we experience is more like an interface, a simplified display masking something far stranger underneath? The evidence comes from quantum experiments that defy common sense, from theories about spacetime that suggest it might not be fundamental, from equations describing reality as pure information rather than matter. These aren't fringe ideas dreamed up by philosophers in armchairs. They're emerging from the same rigorous mathematics and experimental testing that gave us computers, satellites, and medical imaging. The same methods we trust completely when they produce technology now suggest that the solid world they describe might be a kind of projection. You've heard of quantum mechanics making particles behave impossibly, appearing in two places, influencing each other across vast distances, refusing to exist in definite states until observed. But that weirdness no longer stops at the atomic scale. It extends to space itself, to time, to energy, to matter, even to you. The deeper we look, the more the foundations crumble, and what replaces them isn't another solid ground. It's something that looks less like a physical universe and more like a web of relationships, a set of calculations, a process without a permanent home. By the end of this journey, you might find yourself asking a question that once seemed absurd. If space and time emerge rather than exist fundamentally, if particles are merely ripples in invisible fields, if reality itself depends on observation, then who or what is doing the observing? And if no observer exists independently of the system, then what remains? Most of us never stop to question the basic assumption underlying our entire experience. The assumption that there's a world out there, existing independently, whether or not anyone is looking. We touch a table and it resists our hand. We drop a cup and it falls. We glance at the stars and assume they shine in the darkness even when our eyes are closed. This intuition feels unshakable. It's built into how we navigate reality every single day. But here's where the trouble begins. How do you actually know that what you perceive is what's really there? Not what you've been taught, not what seems reasonable, but what you can verify independently of your senses. The answer is uncomfortable. You can't. Because everything you experience, every color, sound, texture, temperature, arrives filtered through a biological system designed not to show you truth, but to keep you alive. Your brain doesn't present the world as it is. It builds a model, a best guess assembled from electrical signals traveling along nerve fibers. Light hits your retina. Sound waves vibrate tiny bones in your ear. Pressure receptors fire in your skin, and your brain interprets all of it, constructing a coherent picture from fragments of raw data. What you see isn't the world. It's a reconstruction, a simulation running inside your skull, optimized for survival rather than accuracy. Take color as an example. The redness of an apple, the blue of the sky, these aren't properties of light itself. Light consists of electromagnetic waves oscillating at different frequencies. There's nothing inherently red or blue about those frequencies. Red and blue are inventions of your visual system, labels your brain assigns to help you distinguish one wavelength from another. Other animals perceive entirely different color palettes, or none at all, depending on their biology. Even among humans, variations in the eye's structure can shift how color appears. What you call red might look slightly different to someone else, and neither of you would ever know. The same applies to sound. Air molecules vibrate, creating pressure waves that ripple outward from a source. But the sound itself, the crash of thunder, the melody of a song, exists only when your auditory system translates those vibrations into something meaningful. Without an ear and a brain to decode the pattern, there's only silence and motion. So the world you think you inhabit, the one filled with colors, sounds, textures, and smells, isn't out there at all. It's in here, generated moment by moment inside the confines of your skull. And that raises a troubling possibility. If your brain is already simplifying, filtering, and interpreting everything you experience, how much of what you perceive is actually real, and how much is just a convenient fiction? Some researchers, including cognitive scientist Donald Hoffman, have pushed this idea further. Hoffman's work suggests that evolution doesn't reward organisms for seeing reality accurately. It rewards them for seeing reality usefully. In other words, your senses didn't evolve to show you the truth. They evolved to show you whatever helps you survive long enough to reproduce. Consider a computer desktop. When you drag a file into the trash, you're not literally moving bits of data across a physical surface. The icon, the trash bin, the folders, all of it is a visual metaphor designed to make complex operations feel simple and intuitive. The real process is happening inside the machine, voltages shifting, transistors switching, electrons moving through circuits, are hidden beneath a user-friendly interface. Hoffman argues that this is exactly how perception works. The colors, shapes, and objects you see are like desktop icons. They're simplified representations of something far more complex underneath, something your brain could never process directly. His team has even run mathematical simulations testing this idea. They created virtual environments where digital agents competed for resources. Some agents perceived reality as it truly was. Others saw simplified, abstracted versions designed purely for efficiency. The result? The agents that saw the truth lost every time. They were outcompeted, outmaneuvered, and driven to extinction by agents that ignored accuracy in favor of survival shortcuts. If this applies to us, and there's no reason to think it doesn't, then everything you perceive might be a convenient lie. The table isn't solid. Your phone isn't really there. The stars, the sky, even your own hands might be front-end visuals masking a back-end system that looks nothing like what you imagine. Even the concept of objects existing in space starts to break down when examined closely. What we call objects, chairs, atoms, even people aren't truly separate, independent entities. They're temporary patterns of energy, structured by invisible rules, constantly exchanging particles and information with everything around them. You breathe in atoms that were once part of other people. The carbon in your cells was forged billions of years ago inside dying stars. At the quantum level, the boundary between you and not you becomes blurry, uncertain, impossible to define with precision. So if your brain shows you a simplified, abstracted world, and that world is made of objects that aren't really objects, and those objects behave like ghosts until someone observes them, then how real is any of this? That's the illusion we're starting to uncover. Not that nothing exists, but that what you think exists isn't what's actually there. What's actually there might not be made of matter, space, or time. It might not be things at all. It might be patterns, relationships, or raw information shaped by perception, filtered by brains, and interpreted by consciousness. And here's where the question becomes unavoidable. If no one is observing, and there's no solid thing to observe anyway, then what's left? Maybe the universe we think we're living in, the one with stars and atoms and galaxies, is just the interface. And maybe behind that interface is something so unfamiliar, so fundamentally different from anything we can visualize, that calling it a universe at all might be the biggest illusion of all. If the universe you experience is only an interface, then the next question cuts deeper. If the icons are not the thing, what is actually out there, if anything at all? To get closer to that, physics forces a shift from how the world feels to how it behaves when examined with extreme precision. And that shift begins with a theory that broke our common-sense picture of reality more than any other: quantum mechanics. Quantum mechanics was not invented to make reality mysterious. It was built to explain stubborn, experimental results that refused to fit the classical picture of solid particles moving along definite paths. At tiny scales, electrons, photons, and other building blocks of matter did not behave like little billiard balls following predictable trajectories. They behaved like something else entirely. Instead of existing in one place with one set of properties, quantum objects seem to occupy many possible states at once, spread out in a haze of probabilities. The mathematical object used to describe this haze is called a wave function. It does not tell you where a particle is. It tells you the likelihood of finding it in each possible place or state if you decide to look. Between measurements, the wave function evolves smoothly according to precise equations. But when a measurement is made, it appears to collapse into a single outcome, one position, one value, one event. This is not just a philosophical story layered onto vague data. The predictions of quantum mechanics have been tested to extraordinary accuracy and have never failed in the lab. The theory underlies modern electronics, lasers, MRI machines, technologies that only work because the quantum description of nature is so precise. Yet that same theory says the fundamental ingredients of reality do not have definite properties until they are observed. The world you interact with emerges out of a cloud of possibilities only when you ask it a question. One of the clearest windows into this strangeness is the double-slit experiment. Imagine firing single electrons one at a time at a barrier with two narrow openings, and placing a screen behind it to record where each electron lands. If electrons were just tiny bullets, you would expect them to form two clusters on the screen, aligning with the slits they pass through. Instead, over time, they build up an interference pattern, bright and dark bands just like waves overlapping in water. The electron seems to behave as if it goes through both slits at once, interfering with itself. The mystery deepens when you try to find out which slit the electron actually used. Place detectors at the slits to track its path, and the interference pattern vanishes. The electrons now behave like ordinary particles, forming two clusters instead of a wave-like pattern. The only thing that changed was your choice to observe the path. The act of measurement did not merely reveal what was already there. It altered the outcome in a fundamental way. So what is real in this experiment? The electron as a localized particle? The wave of probabilities, the interference pattern, or your decision to look? Quantum mechanics does not give a simple classical picture. It gives a set of rules. Probabilities evolve continuously, but measured outcomes are definite, and the bridge between the two remains conceptually mysterious. Attempts to rescue a familiar, objective world from this situation have struggled. One idea was that particles always had definite properties, but hidden variables, unknown details made them appear probabilistic. If those variables could be uncovered, reality would be restored as a fully determined, observer-independent system. In the 1960 seconds, physicist John Bell proposed a way to test this hope using inequalities that any hidden variable theory must obey. Experiments designed around Bell's insight were eventually carried out around the world. They studied pairs of entangled particles, objects whose properties are correlated in ways that quantum theory predicts, but classical physics cannot easily explain. The results violated Bell's inequalities, ruling out large classes of hidden variable explanations. The data forced a stark choice. Either influences can act faster than light, or the idea of a local, observer, independent reality must be abandoned, or both. In other words, there is no deeper layer in which particles carry fixed properties waiting to be discovered in a neutral, detached way. The outcomes you see seem to be inseparable from the way you choose to measure, and from the quantum correlations that tie distant events together. The world at this level behaves less like a collection of independent objects and more like a network of interdependent events. As if this were not unsettling enough, more elaborate experiments push the paradox even further. In a family of setups inspired by John Wheeler's delayed choice ideas, physicists send particles toward a double slit-like apparatus, but delay the decision about how to measure them until after they have passed the critical region. In some versions, the information about which path the particle took can be erased or restored after the fact, altering whether you see an interference pattern or not. The strange conclusion is that the particle's past behavior, whether it acted like a wave going through both paths, or like a particle choosing one, appears to depend on a choice made later in time. The experiment does not allow you to send messages into the past, but it does challenge the simple picture of a fixed history unfolding independently of observation. The act of measurement seems to reach backward, reshaping which story about the particle's journey is true. This suggests that time, like position or momentum, may not be as rigid and one-directional as everyday experience implies. At the quantum level, cause and effect blur. The universe looks less like a film strip with a single predetermined sequence of frames and more like a branching web of potential histories, some of which only crystallize when you inspect them. Zoom in far enough, and the comforting notion of tiny solid pieces of matter scattered through space collapses. Instead of things, you find processes. Instead of objects with intrinsic properties, you find interactions and probabilities. The electron is not a little marble, but a localized excitation of a field. Its position is not a built-in attribute, but a value that emerges when you perform a measurement configured in a certain way. In this picture, reality is not made of independent blocks stacked together. It is woven from relationships: who interacts with what, under which conditions, and with what possible outcomes. The wave function, whether you interpret it as a physical entity or a tool for predicting results, encodes these relationships. What becomes real is always tied to a context, a setup, a question, an interaction between system and observer or apparatus. So when physicists say the universe might not exist in the way we thought, they do not mean that nothing is there. They mean that the classical idea of a world composed of pre-existing objects with fixed properties, sitting in a container called space and evolving along a universal clock, does not survive contact with quantum facts. The underlying structure looks less like a warehouse of things and more like an evolving web of information and correlations. For centuries, the basic units of reality were imagined as particles, indivisible bits of matter flying around in empty space. Modern physics has dismantled that picture. In the framework known as quantum field theory, what truly exists, what the mathematics takes as fundamental, is not particles, but fields that extend throughout all of space. Each type of particle corresponds to a particular field. Electrons come from the electron field, photons from the electromagnetic field, and so on. A particle, in this view, is just a localized ripple in its field, a small bundle of energy that appears when the field is excited in a specific way. An electron is not a tiny ball, it is a pattern, a disturbance, a wave packet in an invisible ocean that spans the cosmos. Different particles are different kinds of ripples, and interactions between them are interactions between fields. This shift is more than a mathematical convenience. It changes what the universe is made of. There are no sharp, unchanging objects at the deepest level, only dynamic patterns in continuous substrates. Even the vacuum, which seems like empty space, is not truly empty. Quantum fields in their lowest energy state still fluctuate, giving rise to measurable effects like the Casimir force between closely spaced metal plates. What looks like nothing is restless, seething with potentiality. If everything is just waves and fields, why does the world feel solid and stable? The answer lies in how these patterns organize at larger scales. Atoms are mostly empty space, but the electromagnetic interactions between their components create resistance when they are pushed together. When your hand presses against a wall, no tiny chunks of matter are literally colliding. Instead, overlapping fields resist further compression, creating a force your nervous system interprets as solidity. This solidity is an emergent effect, not a fundamental property of matter. It arises from the collective behavior of countless quantum events. At everyday scales, these interactions average out into stable structures. Tables that do not collapse when you lean on them, floors that support your weight, planets that hold their shape for billions of years. But underneath this apparent permanence is a restless dance of excitations, constantly forming and dissolving. Identity, too, becomes slippery. All electrons, for instance, are identical not just in practice, but in principle. They are not separate objects with unique labels. They are manifestations of one and the same electron field, appearing again and again in different locations. The distinction between this electron and that electron is a human convenience, not a deep feature of reality. In a very real sense, there is only one electron field expressing itself in many places at once. Even fields, as fundamental as they seem, might not be the ultimate layer. Some theoretical work suggests that quantum fields themselves could emerge from something more abstract, patterns of information, networks of relationships, or purely mathematical structures with no direct spatial form. In these approaches, what we call fields are effective descriptions that work well at certain scales, the way temperature and pressure describe the aggregate behavior of countless molecules. If that is true, then the progression looks like this. Familiar objects emerge from atoms, atoms from particles, particles from fields, and fields from deeper informational or relational structures. At no point do you find a simple, indivisible thing that everything else is built from. Instead, you find layers of organization, each one more abstract than the last. From this perspective, asking what the universe is made of might be the wrong question. It may be more accurate to ask how the universe is structured, what rules govern its patterns, and how those rules give rise to the experienced world of objects, locations, and moments in time. Matter becomes a way of talking about stable patterns. Space and time become ways of talking about how those patterns relate and change. So far, this still assumes a stage, a backdrop of space and time in which fields live and evolve. Classical physics treats space as a smooth continuum and time as a universal clock ticking everywhere in sync. But when quantum mechanics meets general relativity, the theory of gravity that describes how mass and energy curve spacetime, that smooth picture begins to fail. There is a scale, called the Planck length, at which the concepts of distance and duration stop making sense in their usual form. Below this unimaginably small size, attempts to measure position and energy simultaneously inject so much uncertainty that spacetime itself begins to blur and fluctuate. Geometry breaks down into something wild and foamy. The notion of a continuous grid of points, each with a clear location, no longer applies. This has led many physicists to suspect that spacetime is not fundamental at all. Instead, it may be an emergent construct, a large-scale approximation that arises from something deeper when viewed from far enough away. Just as a smooth ocean appears continuous from an airplane, but is revealed as discrete waves and droplets up close, spacetime may be a coarse description of an underlying network of relationships. Some approaches to quantum gravity start from this idea and do not assume space and time at the outset. One such framework is loop-based, in which the basic ingredients are not points in space, but nodes and links in an abstract graph. These nodes represent quantum states, and the links between them represent relationships. From the pattern of connections and their evolution, something that behaves like space can emerge when you zoom out far enough. In this view, you do not begin with a three-dimensional arena. You begin with a web of relations. Distance is not a primitive notion. It is derived from how strongly and in what ways different parts of the network are connected. Space is what the world looks like when the underlying graph is dense and regular enough to approximate a smooth geometry. Other relational ideas extend this further. In some interpretations of quantum mechanics, physical properties do not exist in isolation at all. They only have meaning relative to other systems that interact with them. There is no single, all-seeing perspective from which you can assign definite values to everything at once. Reality becomes a tapestry of perspectives, each defined by interactions, none of them absolute. Time, too, comes under attack. Many of the fundamental equations in modern physics do not contain time as a basic variable. They describe correlations between states rather than events unfolding along a universal timeline. One famous equation in quantum gravity is even called timeless because, in its most natural form, it treats the entire universe as a static whole with all its configurations encoded at once. How then does the sense of flow arise? Some proposals suggest that time emerges from quantum entanglement, the deep correlation between parts of a system. As systems become more entangled and more complex, a direction of increasing disorder appears, which we recognize as the arrow of time. Entropy, the measure of how spread out and mixed the underlying information is, tends to grow, and our experience of past to future tracks that growth. In this view, time is not something that exists independently, ticking away in the void. It is a way of describing change in relational structures, a pattern that arises statistically when enough degrees of freedom interact. There is no master clock outside the universe. There is only the universe's shifting configuration and the stories that can be told about it. Putting these threads together, the traditional picture of the universe objects sitting in space evolving through time begins to dissolve. Matter turns into field excitations. Fields become candidates for emergent behavior from more fundamental information. Space emerges from connections. Time arises from patterns in entanglement and entropy. The stage and the actors are both byproducts of something more basic that does not resemble objects in a room or events on a timeline. This is where the idea that the universe might not exist as a universe comes into focus. The word suggests a container with things inside it, a grand physical arena. But what modern physics increasingly points toward is a vast, interwoven structure of information, relationships, and processes that only looks like objects in space when seen from within, at low resolution, through the limited interface of human perception. You are not merely in the universe, occupying a small region of pre-existing space. You are part of the very pattern that gives rise to space and time in the first place. Your body, your thoughts, your memories are not chunks of matter drifting in a void. They are stable configurations in a sea of interactions, fleeting yet remarkably coherent, like vortices in a flowing river. And if the river itself, space, time, matter is emergent, then the question that once sounded absurd grows impossible to ignore. What, if anything, lies beneath the flow? Right now, the picture forming is already strange. Perception as an interface, particles as ripples and fields, space and time as emergent patterns, rather than fundamental ingredients. But as radical as that sounds, it still leaves a deeper layer of questions unanswered. If the universe behaves more like information than stuff, more like a process than a place, then what kind of structure could possibly give rise to everything you see and feel? The next clue arrived from one of the most extreme objects in the cosmos: black holes. For a long time, black holes were thought of as simple cosmic sinks, regions where gravity was so strong that nothing, not even light, could escape. Drop something in, and it was gone forever. But this created a problem. According to quantum theory, information about physical systems can't simply be destroyed. According to general relativity, anything crossing a black hole's boundary vanishes beyond recovery. Both theories had been tested again and again, and both seemed right. They just could not both be right in this situation. In the 1,970 seconds, work on black hole thermodynamics led to a shocking realization. The amount of information a black hole can store its entropy is not proportional to its volume, as you might expect if information were packed into its interior like items in a box. Instead, it scales with the area of its event horizon, the surface that marks the point of no return. That is, as if everything that ever fell in, everything that ever happened inside, could be completely summarized by data etched on the outer skin. This idea eventually evolved into something broader: the holographic principle. It suggests that in certain kinds of universes, everything happening in a volume of space can be encoded by information living on a lower dimensional boundary. In a hologram, a two-dimensional pattern produces a three-dimensional image. In holographic physics, a theory defined on a boundary can fully describe a higher dimensional world with gravity, particles, and fields. That higher dimensional world becomes, in a sense, a projection of deeper data stored on the edge. The mathematics behind this is sophisticated, but the core message is simple and unsettling. The reality that feels three-dimensional and expansive may actually be a kind of emergent display. The true description of the system could live on a boundary with fewer dimensions, where there is no gravity in the usual sense, only information and its interactions. If the holographic principle applies broadly, then everything you experience, galaxies, stars, your room, your body, could be interpreted as a reconstruction of data written on a distant boundary you will never see. You are not moving inside a vast arena. You are part of a pattern being read from the edge. In this view, location becomes a derived concept. What feels near or far in everyday life might simply reflect how closely related pieces of underlying information are. Two regions that appear far apart in space could be close in the deeper informational geometry, tightly linked in ways that bypass ordinary distance. Conversely, points that seem adjacent might be only loosely connected at the fundamental level. This shift reframes gravity as well. Rather than a fundamental force pulling masses together, gravity can be seen as an emergent phenomenon arising from the way information is organized. The curvature of spacetime, in this picture, is not an irreducible feature of reality. It is how the effective geometry looks when vast numbers of microscopic degrees of freedom arrange themselves in particular patterns. Mass, energy, and the gravitational effects they create become signs that information is distributed in specific ways. The holographic approach has helped physicists reconcile quantum mechanics with gravity in carefully defined models and resolve puzzles about what happens to information in black holes. But it also carries a philosophical cost. If space, distance, and gravity are all emergent from information encoded on a boundary, then the world you know is closer to a computed image than to a solid, independent structure. The idea that information sits at the heart of reality is not limited to holography. Decades ago, the physicist John Wheeler proposed a phrase to capture this possibility: it from bit. The suggestion was that every physical it, every particle, field, or patch of spacetime ultimately arises from binary choices, from yes, no questions and their answers, Reality, at its most basic, might be nothing more than the outcome of countless bits of information being processed. In this perspective, the universe behaves less like a machine made of cogs and more like a computation unfolding according to logical rules. The configurations of matter and energy you see are snapshots of deeper informational states. Measurement becomes an act of extracting bits of posing questions to the underlying system and recording the answers. The familiar world is then the appearance those answers take when viewed through the human perceptual interface. If this is right, then asking what the universe is made of becomes equivalent to asking what kind of information is being stored and how it is structured. The notion of stuff dissolves into patterns of distinctions. This versus that, here versus there, now versus then. The physics you learn in school can then be reinterpreted as an elaborate language for describing how these patterns change. When talk turns to information and computation, it is almost inevitable that one idea surfaces. Maybe the universe is a simulation. Popular culture tends to imagine this as a high-tech version of a video game, with advanced beings or future humans running our reality on some cosmic computer. That image, though vivid, is too narrow and anthropocentric. It treats the deeper level as just another physical world, only with better hardware. The more serious question lurking beneath the simulation metaphor is about structure, not authorship. If a system behaves like a computation, if it processes information according to consistent rules, if it has discrete units, if it has limits on how much data can be stored in a region, then calling it computational may simply be another way of saying it is governed by logical relationships. Whether or not anyone built it becomes a separate question. From this angle, simulation theory becomes less about being trapped in someone's program and more about recognizing that reality has a code-like character. Energy levels come in discrete steps. Quantum states combine and evolve in ways that resemble algorithms. Black hole information bounds act like memory constraints. The universe begins to look like a system where every change can, in principle, be seen as an update to an underlying informational state. Yet even this description may be too comforting. It still imagines a base layer of rules and bits that could, at least in principle, be represented in a machine. But the structures hinted at by quantum gravity, entanglement, and holography may be even more abstract, involving relationships that do not fit neatly into human-made notions of software and hardware. The universe may be computational in a generalized sense without being literally run on anything. Another line of research ties the fabric of space directly to quantum entanglement. Entanglement is the deep connection that can exist between particles, such that the state of one cannot be fully described without reference to the other, no matter how far apart they are. It is not a signal flying back and forth faster than light. It is a shared description that refuses to split cleanly into independent parts. Some theoretical work suggests that if you have a huge number of quantum degrees of freedom arranged in certain patterns of entanglement, something remarkable happens when you examine them from a coarse, macroscopic perspective. A geometry emerges. Distances and directions appear. Curvature arises in a way that matches the equations of spacetime. In this picture, the more two regions of the underlying system are entangled, the closer they appear in the emergent space. Reduce the entanglement, and the effective distance grows. This turns the usual story on its head. Instead of particles being entangled because they once interacted in space, space is what you get when enough entanglement exists. The relationships come first. The geometry shows up later as a convenient description of those relationships. If you could somehow dial entanglement down far enough, spacetime itself would fall apart, leaving only a disjoint collection of degrees of freedom with no meaningful notion of where they are. From that standpoint, the question, "Where is the universe?" becomes slippery. Location is not a fundamental label that can be attached to things. It is an emergent property of how deeply the underlying elements are correlated. You are not a thing placed somewhere in pre-existing space. You are a dense knot in the network of relations that collectively appear as a region of space with a particular shape. Entanglement also provides a window into the origin of time. If space can emerge from patterns of correlation, then perhaps the flow of time can too. Many fundamental equations are time-symmetric or timeless, describing allowed states without specifying a preferred direction from past to future. Yet, your experience is dominated by a sense of irreversible change. You remember yesterday, not tomorrow. You grow older, not younger. One way to reconcile this is to see time as a story told about how information spreads and rearranges. As systems interact and entangle, information that was once localized becomes distributed. Order gives way to disorder, not because a law commands it, but because there are many more disordered states than ordered ones. Entropy increases, and with it emerges the arrow of time. The feeling of a one-way flow may be the brain's way of tracking the steady accumulation of correlations and the loss of recoverable detail. In this sense, the flow of time is not something the universe contains. It is something that emerges when certain conditions are met, when enough degrees of freedom are interacting, when complexity crosses a threshold, when observers arise who can form memories and compare them. Time becomes a way of organizing experiences, not an external river carrying everything along. At this point, the label real begins to strain. On one hand, the world you inhabit is undeniably consequential. Fall from a height, and you will hit the ground. Make a choice, and your life changes. Pain, joy, loss, discovery. These are not illusions in the sense of being inconsequential. They shape you. They matter. On the other hand, the structures that feel most obvious solid objects, continuous space, a single flowing timeline turn out to be high-level outputs of deeper processes. They have the status of a user interface, robust, reliable, tuned for creatures like you, but not revealing the machinery underneath. When physicists suggest that the universe as traditionally imagined might be a kind of hoax, they are not denying the reality of experience. They are questioning whether the picture painted by that experience corresponds to the underlying structure of the world. It may be more accurate to say that there are layers of reality. At one layer, there are rooms, trees, stars, and people. At another, fields and particles, quantum states, and probabilities. Deeper still, entanglement patterns, informational bounds, and abstract relational structures. Each layer is real in its own domain. Each emerges from the one below when viewed at the right scale and through the right lens. For you, the everyday layer is the one that matters most. It is where choices are made, relationships are formed, and meaning is constructed. But understanding that this layer rests on a vast, hidden architecture of information and interaction changes how you relate to it. The world stops being a stage filled with objects and starts looking like a living process, in which you are not just an observer but an expression. If everything you see is an interface, if space and time emerge from deeper patterns, if matter is really excitations in fields or configurations of information, then what does that make you? A cluster of particles? A localized pattern in a field, a self-referential process running on the universe's computational substrate? From the standpoint of modern physics, you are not a separate thing dropped into a pre-existing world. You are a region where the universe has become remarkably organized and self-aware. Your body is a pattern in fields, held together by forces that themselves may be emergent. Your brain is an information processing structure shaped by evolution to navigate a particular slice of reality. Your sense of self, the feeling of being a single, continuous you, is a narrative your brain constructs to make sense of a torrent of internal and external signals. This does not diminish you. If anything, it places you closer to the heart of the mystery. The same processes that generate space, time, and matter also generate conscious experience. The same underlying informational web that gives rise to galaxies also gives rise to thoughts, emotions, and questions like the one driving this entire exploration. What is this universe, really? Seen this way, you are not standing outside the universe, looking in and trying to understand it. You are the universe, in one of its countless configurations, trying to understand itself. And if the familiar universe of objects, distances, and ticking clocks is only one way the underlying structure can appear, then the most disquieting possibility returns with new force. Perhaps there was never a universe in the simple, classical sense to begin with. There is only the deep, shifting architecture of relationships and information and the stories it tells to itself. If space, time, matter, and even your sense of self can all be traced back to deeper patterns and relationships, the next question is no longer just, what is the universe made of? But, which description of it, if any, is actually true? The strange part is that physics does not give only one answer. It offers several competing interpretations and philosophical positions, all compatible with the same experimental data, but radically different in what they say reality is like at its core. For most of history, the default assumption has been a simple kind of realism. There is a mind-independent world out there, made of definite things with definite properties, whether anyone sees them or not. In this picture, Science is a process of gradually uncovering what those things are and how they behave. A table is a table. Planets are planets. Electrons are tiny particles, and the job of physics is to describe them more accurately. Quantum mechanics puts intense pressure on that straightforward view. At small scales, particles do not seem to carry sharp pre-existing values for position, momentum, or other properties. Instead, they are described by wave functions, which encode probabilities. Only when you perform a measurement does a definite outcome appear. Entangled particles behave in ways that cannot be explained by assigning them hidden properties in advance. Attempts to restore a simple, local, realist picture run into conflicts with experimental results. Yet, realism does not vanish. It mutates. Some physicists and philosophers argue for a more abstract realism. The wave function itself is real. On this view, the fundamental stuff of the universe is not particles or fields in space, but the wave function of the entire universe, an object living in a high-dimensional mathematical space. Our familiar three-dimensional world emerges as a kind of effective description of certain patterns within that vast structure. The world is real, but the reality is far removed from everyday intuition. Others hold on to realism by treating fields as fundamental. Quantum fields fill spacetime, and particles are merely excitations of these fields. The fields are taken to be objectively real, regardless of observation. But even here, the probabilities and non-local correlations of quantum theory make it difficult to maintain a picture of sharply localized objects with independent existence. The result is a fractured landscape. Realism survives, but it no longer means tiny billiard balls in a big box. It means committing to some deeper, often highly mathematical entity as what is truly their wave functions, fields, or even abstract information, while accepting that everyday objects are emergent approximations rather than basic ingredients. On the opposite side are anti-realist and instrumentalist approaches. Instead of asking what reality is really like, these viewpoints focus on what the theory actually does. It predicts outcomes of experiments with extraordinary accuracy. From this perspective, the wave function and other quantum tools are not literal descriptions of what exists. They are instruments, algorithms for calculating probabilities. In this spirit, one might say, there is no need to imagine that a particle is in many places at once. The wave function is simply a device that tells you the odds of finding it here or there when you look. Talking about its real state between measurements is adding metaphysical baggage that the theory neither requires nor justifies. Some formulations of quantum mechanics, such as the most minimalist versions of the so-called Copenhagen-like view, lean in this direction. They treat measurement as a primitive notion and avoid making claims about what happens when no observation occurs. Reality, in this sense, is defined operationally. It is the regularity in our experiences and the outcomes recorded in experiments, not a hidden structure beneath them. This can feel unsatisfying, especially to those who want a clear picture of what the universe is. It avoids certain paradoxes by refusing to ask questions that the formalism is not designed to answer. But it also sidesteps the need to radically reshape our intuition about what exists. Instead of saying the universe might not exist, it says the task of physics is not to say what exists, but to describe what we can observe and predict. Another bold strategy is to take the quantum formalism completely at face value and never introduce a special rule for measurement at all. In this view, the wave function evolves smoothly and deterministically according to the Schrödinger equation without ever collapsing. Every time a measurement-like interaction occurs, the universe's state branches into components corresponding to each possible outcome. This is the essence of the many worlds interpretation. When you measure a quantum system that could yield result A or result B, both outcomes occur but in different branches of the universal wave function. In each branch, observers see a definite result and experience a consistent history. They are unaware of the other branches, which are just as real but inaccessible. Under many worlds, there is no fundamental randomness. There is only the branching structure of the wave function. Probabilities reflect how amplitude is distributed across branches and how likely an observer is to find themselves in one branch versus another. Reality is fully real, but stupendously large and constantly splitting. The cost of removing collapse is embracing a picture in which every quantum event spawns new, non-communicating versions of the universe. This is a deeply realist view. The wave function is the real thing, and the multiverse is literally there. but it comes with a heavy philosophical price. It forces you to accept an enormous amount of unobservable structure in exchange for a clean, equation-driven picture of reality. Some alternatives shift focus from things to relations. In relational approaches, physical properties do not exist in isolation. They exist only relative to other systems. For example, the spin of a particle is not an absolute attribute. It carries everywhere. It is a value that becomes meaningful only in relation to a particular measuring device or observer. From this angle, there is no single, godlike vantage point from which all properties have definite values simultaneously. Instead, reality is a network of interactions. Each interaction defines certain properties relative to the systems involved. What is true for one observer, what outcome they record may differ from what is true for another. And there is no higher-level view from nowhere that reconciles them into a single absolute story. This does not mean that anything goes. The interactions obey strict rules and different perspectives must agree where they overlap. But it does mean that asking, what is the particle really like on its own, may be a category mistake. There is no on its own. There are only webs of relations. A related, though distinct idea is that reality has a participatory aspect. In some philosophical and semi-formal interpretations, observations are not just passive recordings of pre-existing facts, but active events that bring specific outcomes into being. The universe is not a finished book waiting to be read. It is a story co-authored by the questions that are asked and the interactions that occur. Meanwhile, holographic and entanglement-based approaches suggest a different kind of competition not between worlds, but between levels. In these pictures, the three-dimensional universe is not fundamental. It is an emergent phase of a deeper system described more naturally in terms of information, correlations, or lower dimensional boundaries. One can adopt a realist stance at the emergent level space. Fields and particles are real enough for the scales where they apply while reserving true fundamentality for the hidden layer of entangled degrees of freedom. Or one can treat the emergent world as a kind of useful appearance, insisting that only the underlying informational structure deserves to be called real. Either way, the traditional notion of a universe as a big container filled with stuff is challenged. If everything inside can be recast as data on a boundary or as patterns of entanglement, the difference between physical and informational begins to erode. The holographic principle becomes not just a technical tool, but a philosophical lens through which the universe looks more like a codebase than a collection of objects. Simulation ideas sit somewhat orthogonally to these interpretations. They do not change the equations of physics, they change the story about what those equations mean. A simulated universe could, in principle, exhibit quantum mechanics, holography, emergent spacetime, and all the rest. The simulation hypothesis is a statement about the origin and status of those laws, not about their structure. From a strict scientific point of view, this makes the simulation idea hard to test. If the simulation is perfect, there may be no direct signature that distinguishes it from a base reality. Some speculative proposals suggest that subtle anomalies, limits on resolution, unexpected noise patterns, or deviations in high-energy physics could betray an underlying discrete grid, like pixels in a rendered world. But so far, there is no widely accepted empirical evidence pointing decisively in this direction. As a philosophical position, simulation theory fits naturally with the information-centric view. If the universe is fundamentally computational, the notion that it could be implemented on some deeper substrate becomes easier to imagine. Yet even here, physics remains neutral. The equations care about how states transform, not whether someone wrote the code. Hovering over these debates is a question that physics alone has not yet answered. What about consciousness? If everything reduces to quantum fields, entanglement, and information, how does the raw feeling of experience arise? How does a pattern of interactions become a point of view? Some thinkers argue that consciousness itself must be woven into the fabric of reality at a fundamental level, on par with space, time, and matter. Others maintain that it emerges from sufficiently complex information processing in physical systems like brains. From that standpoint, experience is what it is like for the universe to implement certain highly organized patterns. What unites these positions is the recognition that any complete picture of reality must account for the fact that there is something it is like to be you. A purely external description fields, equations, geometries capture structure, but leaves out the first-person perspective. Whether consciousness ultimately forces a revision of physics or can be fully assimilated into its existing framework, remains an open question. In the midst of these competing views, realism, anti-realism, many worlds, relational interpretations, holographic frameworks, and simulation ideas, where does that leave you? It might be tempting to see this as a purely academic dispute, interesting but detached from daily life. But the way you think about reality inevitably shapes how you think about yourself. If you lean toward a robust realism, you might feel anchored by the idea that there is a definite structure out there. Even if it is vastly more abstract than tables and chairs, you become an expression of that structure, a local manifestation of universal laws. Your choices, experiences, and relationships are ways in which the underlying reality unfolds. If you gravitate toward more relational or instrumental views, you might see the world less as a fixed sculpture and more as an ongoing conversation. Properties exist in interactions, not in isolation. Truth is not a static inventory of things, but a network of consistent perspectives. You, as an observer and participant, are part of what makes certain aspects of reality concrete. If holographic or informational pictures resonate, you might come to see yourself as a pattern in a vast data structure, a coherent configuration in an ocean of possible states. Your life is not a path carved through an external space, but a particular trajectory in the space of relationships and correlations. Identity becomes less about what you are made of and more about how you are organized. And if simulation or computational metaphors appeal to you, you might think of yourself as a process rather than a thing, a self-aware subroutine in a cosmic flow of computation. Meaning, then, is not something imposed from outside, but something generated from within the process itself. All these perspectives share one consequence. They loosen the grip of the naive picture in which the universe is just out there, solid and self-contained, independent of observers, interpretations, or underlying informational structure. The ground you thought you were standing on turns out to be a platform built from countless invisible supports, quantum rules, entangled states, emergent geometries that can be described in profoundly different ways. Yet this does not leave you floating in nothingness. The world of your experience is still consistent and reliable enough to build lives, relationships, and civilizations on. Gravity still holds you to the earth. Technology still works. Your choices still ripple through the web of interactions that constitute your life. What changes is not the day-to-day reality you navigate, but the depth at which you understand what it means for that reality to exist at all. When scientists say the universe might be a hoax, they are not claiming that everything is fake. They are pointing out that what you see is not the whole story, that the interface you inhabit conceals layers of structure so strange that calling them a universe, in the old sense, might be misleading. What lies beneath could be fields, wave functions, entanglement graphs, holographic codes, or something still beyond imagination. And yet, whatever that deeper structure is, it has given rise to you. A conscious pattern capable of asking these questions, of feeling awe, confusion, curiosity, and wonder. In the next stretch of this journey, the focus turns directly to that you. If the world is a network of processes and information, what does that do to your sense of self, free will, and meaning? What happens to identity in a universe that might not be a universe at all? If the universe you move through is not fundamental, if space, time, and matter are all emergent from deeper patterns, then the most personal question suddenly becomes unstable. What, exactly, are you in a world like this? The old answer is simple. You are a body in space, living out a sequence of moments in time. But if that body is a pattern in fields, if that time is a way of reading, changing information, then your identity becomes less about what you are made of and more about how you are organized and experienced. From a modern physics perspective, your body is not a solid object, but a remarkably stable configuration in a restless sea of fields and interactions. The atoms that make you up are mostly empty space. The particles composing those atoms are excitations of fields that stretch across the universe. The matter of you is constantly being exchanged with the environment through breathing, eating, drinking, and radiating heat. Over time, nearly every atom in your body is replaced. Yet through all of this, there is continuity. You do not feel yourself flickering in and out of existence. You experience a steady, ongoing sense of being you. That continuity is not anchored in a fixed set of particles. It is anchored in patterns, how information flows through your brain, how memories are stored and updated, how your nervous system integrates signals from the world and from within. In this sense, you are closer to a process than a thing. A whirlpool in a river has shape, structure, and persistence, but the water inside it is always changing. Likewise, your identity is the stable form of an evolving pattern in a physical and informational substrate. The fields, particles, and atoms provide the raw material, but the you that experiences the world is the pattern they temporarily form. Earlier, perception emerged as a kind of user interface, an evolved model that summarizes hidden complexity in a way that helps you survive. Your brain is not showing you the universe as it is. It is showing you a usable version, a low-dimensional, compressed representation tailored to the needs of a biological organism. That same modeling applies inward. Your brain does not only construct a picture of the external world, it constructs a picture of you. It tracks your body, your position, your goals, your memories, your social connections. It weaves these elements into a narrative that feels like a single, unified self traveling through time. This narrative is incredibly useful. It lets you plan, learn from the past, and imagine possible futures. But like all models, it can be incomplete or distorted. You are aware of only a tiny portion of the neural activity that maintains your sense of self. Under certain conditions, meditation, trauma, brain injury, psychedelic states, that sense can shift dramatically. People report feeling as if the boundary between themselves and the world dissolves, or as if they are observing their life from the outside. These experiences do not prove any particular metaphysical claim, but they hint that your ordinary sense of being a discrete, sharply bounded I is one possible configuration among many. It is a mode your brain runs, not an unchanging fact about reality. If the universe is governed by laws, whether deterministic equations or probabilistic quantum rules, where does that leave free will? On one extreme, if everything is strictly determined from initial conditions, then in principle, every choice you make was already implicit in the state of the universe long before you were born. On the other extreme, if quantum events inject genuine randomness, that alone does not magically create freedom. A random flip is not the same as a free decision. A more nuanced view looks at levels. At the microscopic scale, particles or fields follow rules. But at higher scales, new patterns emerge: molecules, cells, brains, societies. These complex systems can exhibit behaviors that are not obvious from the underlying laws. Your brain, as far as current science can tell, implements decision-making processes that integrate vast amounts of information, compare options, and select actions based on goals, values, and memories. In this layered picture, free will is not a violation of physics. It is a way of describing what happens when a highly organized system, like a human brain, exerts top-down influence on its components. The same physical laws that apply to everything else also govern your neurons. But the organization of those neurons enables you to deliberate, reflect, and choose. Your sense of agency is real at the level where it operates, even if, at a deeper level, it can be described in terms of dynamics and information. If the universe is not what it seems, if it might be a holographic projection, an emergent computation, or an intricate web of entanglement and relations, does that drain meaning from your life? It might seem that way at first. If everything is just information, just patterns, just emergent, it is easy to hear that just as a dismissal. But emergent does not mean unimportant. The meaning of a book does not reside in the paper and ink, but in the patterns they form and how a mind interprets them. The significance of a piece of music is not in the air vibrations alone, but in the structure of the sound and the experience it creates. In a similar way, the value of your life does not depend on the universe being made of solid stuff. It depends on the patterns of relationship, consciousness, and experience that arise. In fact, realizing that everything is connected at a deep level, that you are woven into the same underlying fabric as stars, galaxies, and quantum fields can intensify meaning. The atoms in your body were forged in ancient stellar furnaces. The information patterns in your brain are part of a cosmic story that began long before you and will continue long after. Your personal narrative is a local chapter in a far larger unfolding. For centuries, humans placed themselves at the center of the story. First, the Earth sat at the center of the cosmos. Then, after that idea fell, our species still seemed central, uniquely chosen, separate from the rest of nature. Modern science has steadily eroded that specialness. The Earth is one planet among billions. The human species is one branch of the evolutionary tree. Our sun is one star in one galaxy among trillions. The picture emerging from physics goes further. Not only are you not at the spatial center of the universe, you are not even in a privileged ontological category. The same kinds of processes that generate stars and galaxies also generate life and consciousness. There is no sharp dividing line between inert matter and living beings when viewed through the lens of fields, information, and emergent patterns. There are just different levels of organization and complexity. This can feel humbling, even destabilizing, but it also dissolves a deep loneliness. You are not an isolated self trapped in a foreign universe. You are the universe, configured in a way that allows for self-awareness, curiosity, and care. The separation between you and everything else is a useful boundary at one level, but at a deeper level, it becomes porous, provisional, and fluid. Everyday life in an unreal universe. What does all of this mean for ordinary life? Tomorrow, you will still wake up to an alarm, check your messages, talk to people, make choices, and face problems that have nothing to do with holography or quantum gravity. The rent is still due, loved ones still matter, pain still hurts. The key insight is not that everyday concerns are trivial because the universe is strange. It is that everyday concerns gain a new dimension when seen against the backdrop of that strangeness. Arguments, anxieties, and routines are happening inside an unfathomably intricate structure that might ultimately be describable in terms of pure information and relational patterns. The fact that such a structure can generate the taste of coffee, the sound of laughter, the ache of grief, and the thrill of discovery is itself astonishing. Knowing that your perceptions are an interface can make you more cautious about assuming that how things appear is how they are. It can encourage humility about beliefs, openness to new ideas, and curiosity about other perspectives. Recognizing that you are a process rather than a fixed object can soften rigid identities and make change feel more natural. Understanding that you are part of a larger, interconnected system can deepen your sense of responsibility toward other beings and the environment. Few questions probe the meaning of reality as sharply as death. If you are a pattern, what happens when that pattern dissolves? At a physical level, the answer is simple. The organization breaks down. The body decays, its components return to the environment. The fields that once sustained your pattern continue to exist, but the particular configuration that was you no longer persists. At an informational level, traces remain, memories in the minds of others, records, creations, and impacts on the world. The pattern continues indirectly, diffused into the larger network. And at the deepest level, the underlying fabric of relationships and information is unchanged. The universe has not lost any capacity. It has simply reconfigured one of its many temporary forms. This does not resolve the existential weight of mortality, but it reframes it. The fear often rests on the idea that there is a sharp, absolute divide between existence and non-existence, between being and nothing. In a reality made of evolving patterns, that sharpness softens. You are not a self-contained object that suddenly stops. You are a wave that rises, crests, and falls back into the sea it came from. If everything is deeply connected, if space is built from entanglement and matter from fields, then the boundary between self and other is partly a matter of perspective. At the level of experience, that boundary is essential. Without it, you could not function. You need to distinguish your body from its surroundings, your thoughts from other voices, your responsibilities from those of others. But at deeper levels, that line blurs. The atoms in your body were once part of stars, rocks, plants, and other organisms. The information in your brain has been shaped by culture, language, and interactions with other minds. Your choices ripple outward, affecting people you will never meet. You are a node in a global and cosmic network, constantly exchanging matter, energy, and information. Seeing yourself this way can transform how you relate to others. Compassion, cooperation, and empathy can be understood not just as moral ideals, but as natural expressions of an underlying connectedness. Hurting others ultimately hurts the network you are part of. Helping others strengthens the structure that sustains you. One of the most profound implications of this whole picture is that consciousness, your capacity to experience, reflect, and wonder, is not an accidental side effect tacked onto an otherwise meaningless world. It is a feature of how the universe's deep structure can manifest under the right conditions. Stars form, fuse elements, explode, and seed new systems. Planets arise, cool, and develop complex chemistry. Life emerges, evolves, and learns to sense and act. Nervous systems appear, grow more intricate, and eventually become sophisticated enough to ask questions like, what is all of this? When you contemplate the nature of reality, the universe is not just being observed. It is, in a sense, observing itself. This does not require any mystical assumptions. It follows directly from the recognition that you are not separate from the world you study. Your brain is made of the same stuff, governed by the same laws, embedded in the same informational fabric. When insight happens, it is the structure of reality becoming aware of one more aspect of itself. If you are enjoying this journey into the nature of reality, consider subscribing to our channel, Broken Zach, so you don't miss what comes next. After all of this, it might be tempting to search for a final answer, a single sentence that declares what the universe really is and what you really are. But the current frontier of science does not offer that kind of closure. Instead, it offers a collection of powerful, sometimes conflicting frameworks that all illuminate different facets of the same underlying mystery. You have learned that perception is an interface, not a window, that matter is patterns and fields, that space and time may be emergent, that information and relationships may be more fundamental than objects. That reality might be holographic, computational, relational, or some combination of these, and that your own sense of self is a story embedded in and generated by this vast architecture. None of this erases the reality of your experience. It enriches it. It reveals that every moment of awareness is perched on top of layers upon layers of structure and process, most of which are invisible, but all of which are active in making this moment possible. In the final part of this journey, the focus turns back outward. If the universe might be a hoax in the classical sense, what does it mean to look up at the night sky, to feel awe at distant galaxies, to search for meaning in a cosmos that may be more like a computation than a container? And is there a way to hold both truths at once? That the world you see is not what it seems, and that it still matters more than ever? Every night, above the glow of cities and the quiet of sleeping streets, the sky sends you a message. A scattering of stars, a wash of darkness, perhaps the faint arch of the Milky Way if you are lucky. For most of human history, that sight was taken at face value. Distant suns in a great black dome, lanterns hung in the heavens, or faraway worlds in a vast physical void. Today, after centuries of physics, cosmology, and philosophy, that same sky carries a different question. Not just what is out there, but what does out there even mean? When you look up, your eyes receive a trickle of ancient light. Photons that left stars millions or even billions of years ago finally reach your retina. Your visual cortex translates those signals into points of brightness against a backdrop of darkness. It feels direct and immediate, as if you are seeing the universe itself laid bare. But by now, you know that is not what is happening. Your brain is constructing a model, compressing complex physical processes into a simple, navigable picture. The stars are not where they appear to be. Some may already have died. The distances you imagine are conceptual shortcuts laid onto something far stranger than a three-dimensional void. The night sky you experience is an interface, a useful, beautiful visualization of phenomena filtered through human perception. That does not make it fake. It makes it functional. The patterns of constellations guided sailors, farmers, and storytellers long before anyone knew about galaxies or space-time curvature. Even if the underlying reality is a holographic projection or a web of entanglement, the sky you see is a stable, meaningful slice of that structure. It is the way the deeper architecture appears to a brain like yours, living on a small planet around an ordinary star. Does awe survive in a universe that might be emergent, informational, or even computational? The answer depends on what you think awe is for. If awe relied on the universe being made of solid, indivisible stuff, then learning that everything is fields, patterns, and relations might diminish it. But awe is not tied to any particular ontology. It is the response of a finite mind confronting an apparently inexhaustible depth. In some ways, the modern picture can amplify that response. Consider that every star you see is powered by nuclear fusion, governed by quantum rules and fundamental forces. The atoms in your body were forged in such stars and recycled through countless cosmic events. The same fields that ripple to create distant suns also ripple to create the neurons firing in your brain as you contemplate them. The story is not simply you looking at the universe, it is the universe in one form looking back at itself in another. If the cosmos is holographic, then those stars may be emergent features of an underlying informational boundary. If space is woven from entanglement, then the distance between you and a galaxy millions of light years away is, at a deeper level, a statement about how correlated certain degrees of freedom are. These reinterpretations do not erase the grandeur of the scene. They intensify it, revealing layer after layer of structure beneath a single moment of stargazing. Throughout this journey, the phrase, "the universe might not exist," has been a provocation. Taken literally, it sounds absurd. Clearly, something exists. You experience sensations, make choices, and interact with a world that resists your will in consistent ways. Tables hold weight. Fire burns. The sun rises and sets whether you notice it or not. What the phrase really challenges is not existence itself, but a particular picture of what existence is like. The classical universe, a big three-dimensional container full of solid objects with fixed properties, all evolving along a universal clock, is the thing under scrutiny. Quantum mechanics, field theory, holography, and emergent spacetime all suggest that this picture is, at best, an approximation. Useful? Yes. Fundamental? No. But usefulness is not a small thing. At the scale of everyday life, the classical picture works well enough to build bridges, design spacecraft, and plan your week. The fact that deeper layers of reality operate differently does not cancel the reality of those achievements. It simply places them in context. The world of streets, trees, conversations, and feelings is real enough for the purposes that matter most to you, even if it is not the ultimate basement level of the cosmos. The challenge, then, is to hold two truths at the same time. One truth: the world you inhabit is an interface. Your perceptions show you a distilled, specific rendering of an underlying structure that is almost certainly nothing like what it appears to be. Objects are mostly empty space. Matter is patterns and fields. Space and time may emerge from information and entanglement. The classical universe may be a hoax your senses play on you, a necessary illusion crafted by evolution. The other truth: the interface is where you live, where meaning is made, where joy and grief and love occur. The fact that your experience is the output of deeper processes does not make it less significant. On the contrary, it means that the deepest structures of reality support the existence of beings who can ask questions, care about answers, and change the course of their own stories. You do not have to choose between these truths. You can recognize that your everyday world is an emergent layer and still treat it as the stage on which your life unfolds. You can study the equations that describe fields and entanglement and still be moved by a sunset or a piece of music. You can know that your sense of self is a construct and still act with integrity, courage, and compassion. Once you see yourself as part of an interconnected fabric, responsibility takes on new weight. Your actions are not isolated events carried out by a detached individual. They are modifications to the network of relationships that defines you and your world. Every word you speak, every choice you make, reshapes that network in ways that can echo far beyond your immediate surroundings. If the universe is informational at its core, then what you do is not just moving matter around. It is editing the pattern. You alter the flow of energy, the distribution of information, the trajectories of lives. From this viewpoint, ethics becomes less about obeying rules handed down from outside and more about understanding consequences inside a shared structure. Harming others damages the fabric that sustains you. Helping others strengthens it. Curiosity, creativity, and learning refine the interface, making it possible to perceive and express more of the universe's potential. Indifference and cynicism narrow it, flattening complexity into numbness. In a reality where everything is connected, your role is not optional. You are always participating, whether consciously or not. Calling the universe a hoax can be misleading if it suggests malicious intent or a prankster behind the scenes. A better way to hear it is as a reminder: the way things appear is not the whole story. The solidity, separateness, and simplicity of the classical world are, in a sense, tricks, but they are also invitations. They invite you to look closer, think deeper, and question assumptions that once seemed beyond doubt. The discovery that the Earth orbits the sun did not make the sunrise less beautiful. It made it more meaningful, revealing the hidden motion behind a familiar sight. In the same way, Learning that the universe may be emergent from information, fields, and entanglement does not make your life less real. It opens a door to a richer understanding of what it means to exist at all. You are not being asked to abandon the world you know. You are being invited to view it as one layer in a larger, more intricate reality, one in which your existence is both fragile and astonishingly unlikely, yet grounded in the same principles that shape galaxies and quantum fields. In the end, no current theory tells the entire story. Quantum mechanics, general relativity, quantum field theory, holography, emergent spacetime, information theoretic approaches all are powerful. All are incomplete. Each illuminates a part of the puzzle while raising new questions. The most honest position is not to pretend that science has finished its work, but to recognize how far it has brought us and how much remains unknown. You stand in that unknown every moment. You stand in it when you look up at the night sky. You stand in it when you feel a surge of emotion you cannot fully explain. You stand in it when you make a choice that changes your life in ways you could not foresee. The mystery is not somewhere else, at the edge of the observable universe. It is right here, woven into every perception, every thought, every breath. To live with that mystery is not to give up on understanding. It is to let understanding and wonder coexist. It is to let equations and awe share the same mental space, each revealing something the other cannot. If the universe you see is a kind of interface, then perhaps the most profound act is to use that interface well to learn, to care, to create, to explore, to honor the layers of reality you can grasp while remaining open to the possibility that the deepest layer may always exceed the reach of any theory. You do not need a final answer to live a meaningful life in such a cosmos. You need only this: the willingness to keep looking, to keep questioning, and to keep being astonished that there is anything here at all, let alone a universe that can wonder whether it exists. If you enjoyed this video, watch this one too. It's a great one, and we'll see you in the next video.